So FRQ1 asks us to prove that the rotational inertia of the solid cylinder is 1/2 mr squared. And we're going to use a given formula, which is inertia equals integral of r squared with respect to m, which is true for any continuous body, which is a solid cylinder. And another relationship we can use is that since we know that the density of the cylinder is uniform, then this relationship will also be true. P is density equals mass over volume, which gives us density. This is a constant ratio, so if mass over volume, it will also equal dm over dv because the ratio is the same. So we want to isolate. We have dm here. We also have dm here. So we're going to want to isolate for dm. So we dm equals m over v times dv. We can go ahead and plug that in. Inertia equals integral of r squared. Dm, which is going to be mv dv. And now we still can't integrate yet because this has to be with respect. The variables have to be the same. So we're going to have to find a different relationship for dv. And to do that, we're going to look at just one portion of the cylinder. Imagining it's like a shell. So each shell continuously gets, the radius of the shell gets bigger and bigger, overlaying on top of each other until it forms like a solid cylinder. So if we look at that shell from a top view, it'll sort of look like this. Like a really thin shell. The thickness obviously won't be this big. It's like a really like thin shell. So if we kind of unravel this shell, it will be a straight. This is a top view. It will be a straight like sheet of paper, and we can use that sheet of paper to find a relationship for volume. So we're gonna, instead of this is a top view, now we're gonna make it a side view of the sheet of paper. Kind of like this. So we know that, and if you imagine that this sheet of paper has like sheets within it, we can use that to find the volume of the paper. So let's say the surface area, if we keep adding more and more sheets of paper, we'll find the volume of this thin sheet of paper. So the surface area, integral of the surface area with respect to the thickness, which is d, we'll denote that as dr. Like we add all of that up, the individual surface areas, until we get like a shell. It's going to equal to, that'll give us the volume of the shell. So we want to find dv, so we can get rid of the integral, and this will be dv. So it'll be a dr equals dv, and we know that a is length times width, so we have a length here, which we know is given as L, because that's the length of the cylinder, and its width here, when we looked at it earlier from a top view, it would be the circumference of the shell, and we know circumference is given as 2 pi r. So area equals L times 2 pi r, and we'll plug that into here. L times 2 pi r times dr, which is the thickness, equals dv. And now that we have this relationship, we can plug it into here. Inertia equals integral of r squared m over v times L times 2 pi r times dr. And now we can integrate because this variable is the same as this one. And also when we integrate, we can take out all the constants that we know. So we know that m and v is a constant, L is a constant, and 2 pi is a constant. So those will be all on the outside. L times 2 pi, and r is going to be on the inside with dr. We can integrate that. That'll give us r squared over 2. Oh, sorry, earlier this is an r. There's another r squared here that it's going to be r to the power of 3, because r times r is going to equal to the power of 3. So if we have r3 and we integrate that, it's going to be r to the power of 4 over 4. So that is the equation that we have. And now we can find v. We can plug in a different equation for v here. So using the derivative of v, if we integrate it, we integrate both sides, we can find v. So again, L and 2 pi are constants, so we can take that out, and we're just integrating r dr, which is going to equal L times 2 pi. Integration of r is going to be r squared over 2. So we have that, and we're going to plug it back into v here. So I equals m over L times 2 pi times r squared. And you see there over 2, these 2's cancel out. And continuing, we still have times L times 2 pi times r 4 over 4. There's more stuff that we can cancel out. So we can cancel out L here and L here, and a pi here and a pi down here. So we're left with I equals m times, and also the 2 and the 4, they'll cancel out so that the 2's gone, and what's left down here is just, the 4 is left, it's just a 2, and the r squares and the r to the power of 4 can also cancel out, so the r squared will be gone, and we'll be left with an r to the power of 2. So it'll be m times r to the power of 2 over 2, and that is equal to what we were trying to prove is 1/2 m r squared. So that's part A of FRQ1, and now we're going to move on to part B. So part B1, it asks us to calculate the linear acceleration of the block. So to do that, we're going to have to use two, we're going to have a Newton, or a linear acceleration, and angular acceleration. So in the linear, we can use net force equals mass times acceleration. And this is, we're going to be looking at the block for this one. So the net force on the block is just the force of gravity of the block, which is mg, pulling it down, and also the tension that is opposing it, that is wrapped around the cylinder. So mg minus t equals mass of the block times acceleration. So we're gonna isolate for t. So we move t to the other side, and we move mg and ma together. So it'll be t equals mg minus ma. And then so now that we have that, we're gonna move to the rotational aspect. So with that, we'll have, sorry, not angular, rotational. With that, we'll have net torque equals inertia times angular acceleration, which is alpha. And relationships that we know is that torque is equal to the tension acting on the cylinder times the distance that the tension is perpendicular from the axis, which happens to be the radius of the cylinder. And inertia, as we found earlier, is just 1 or 1/2 mr squared. And angular acceleration is equal to linear acceleration over the radius. So we have those, we're going to plug that into there. So torque is T times tension times R equals 1/2 mr squared times A over R. And we see here, we can cancel out all the R's. The R on this side and R at the bottom will cancel out the R squared here. So we're left with T equals 1/2 m. This is going to be mass of the cylinder, not mass of the block. So mass cylinder, and then the linear acceleration of the whole system. And now that we have two T equations, we can set them equal to each other. So mg minus ma is equal to equal to 1/2 mass of the cylinder times acceleration. And so we're going to move all the variables to similar variables to one side. So we're going to move ma to this side. We're left with mg, which is the mass of the block, equals 1/2 mass of the cylinder times acceleration plus mass of the block times acceleration. So we're going to factor out, and so that we can have a by itself. So we'll have mg on this side equals 1/2 mass of the cylinder plus mass of the block, and then a is by itself here, or yeah, a is by itself. So we can divide, go ahead, divide both sides by this. I'll get a different sheet of paper. So we have, now we just have mass of mg, which is force of gravity of the block, divided by 1/2 mass of the cylinder plus mass of the block is equal to linear acceleration of the system. And we're going to go ahead and plug in everything that we know. Mass of the block is 2 kilograms times gravity is 9.8 over 1/2 mass of the cylinder is 2.5 kilograms plus the mass of the block again is 2 kilograms. So A, we plug all that into calculator and we'll get that A equals 6.031 meters per second squared. That's a linear acceleration of the system. And now for part 2 or part B2, it's asking us to calculate the net torque exerted on the cylinder. So we had a equation up here for torque already. Was that net torque equals inertia times angular acceleration, which you know can be broken down into inertia can be broken down to 1/2 m of a mass of the cylinder times r squared times a over r, which is what angular acceleration is. We can go ahead and cross out r at the bottom here and one of the r's here, so we're left with only one r in the equation, and then we plug in everything we know, so that net torque will equal 1/2 mass of the cylinder, which is 2.5 kilograms, and then the radius of the cylinder, which is 0.4 meters, times the acceleration, which we just found to be 6.031. This is the linear acceleration. We plug all that into the calculator, we'll get the net torque equals we'll get that net torque equals 3.016 newtons per meters. And then for part 3 of B3, it's asking us to find the tension in the string. And we also already have a relationship for that, which is T equals mg, mass of the block times gravity minus mass of block times acceleration. So we'll write that again, T equals mg minus ma. We'll plug in everything we know. T equals mass of the block, which is 2 kilograms, times gravity is 9.8, minus, again, the mass of the block, 2 kilograms, times acceleration, which we found earlier to be 6.031 meters per second squared. We'll plug all that into the calculator, we'll get that T equals the tension equals 7.538 newtons. So that's it for part B, and we're going to move on to part C, which asks us to graph the angular momentum of So we'll draw out the graph first, which is on the vertical axis we'll have L, which is angular momentum, and on the horizontal we'll have time. And here is TS, which is given as the time when the block reaches its lowest point and the string has completely unwound. So we know that since acceleration is constant at 6.031, the velocity will also be constant. And angular momentum is equal to inertia times angular velocity. And because this is a proportional relationship, and we also know that angular velocity is just linear velocity over radius, this is also still a proportional relationship. So if velocity is increasing, then angular momentum will increase proportionally. And since we know that velocity is increasing with the constant acceleration, then the velocity will look like a straight linear line as it's increasing. And once it hits the point where the string completely unwounds, the cylinder will start to rewind itself, but this time, because acceleration is now opposing its motion, the momentum will be decreasing, still linearly because acceleration is constant. So that's part C. And then part D asks us what if the solid cylinder is replaced with a hollow cylinder? And will it take longer for the block to reach to unwind completely or less time? So we know that a hollow cylinder will have a greater inertia because at the same mass with the same mass if it's hollow, then that amount of mass will be distributed further from the axis, so the inertia will be greater. Will be distributed further from the axis of rotation, making the making R greater, so that the inertia of a hollow cylinder will be greater than a solid cylinder. So since the exact same force is still acting on the system as a whole, which is just the force of gravity of the 2 kilogram box, same force is acting. Cylinder, acceleration of the system will be less because the same force has to act on a greater inertia, which means there will be more resistance, so it won't accelerate as fast. So that means that if acceleration is less, the acceleration with the hollow cylinder is less than with the solid cylinder, it will take a greater time. It will take a longer time for the block to completely unwind, because it's traveling the same distance with a slower acceleration. So we can conclude that time the time for the block to travel that distance when the cylinder is hollow will be greater than when the cylinder is solid, because the hollow cylinder has a greater inertia, resulting in acceleration to be less. So that is it for FRQ 1.